Good morning, everybody. We are plugging right along. Like I said in the last video, I do feel that we're kind of on that downhill side where things are going to be really easy. Then they're going to kind of start getting difficult, and then we're going to find that they're easy again. Here we're going to start introducing sampling error. And initially, with what we're looking at today, it is one of those relatively simple things. It's a lot of just basically interpretation and just some intuitive thought about how this works. And then as we progress through sampling error, not today, but in later segments, we will see that there's a lot of mathematics involved in trying to compute sampling error. So when we talk about sampling error, this is something we kind of hinted at just a little bit when we first started this course. If you take a sample of a group, and I kept referring back to if we just sampled our classroom is not 100% representative of the entire student body at Perry Central High School. So there is some error naturally associated with taking a sample of a population because you're going to miss a few things. You're going to miss a few different representations of people. You're going to overrepresent some groups of people or whatever the case might be that you're studying. So I think back to one of our examples, I believe in the last set of notes, when we talked about assessing normality. We were talking about the pounds of chicken that people consume in the U.S. and there was that one value in there that was 0, and then we threw that point out. But that was just for that particular sample because obviously there's going to be more vegetarians in the United States than just that one person. It just so happened that in that particular sample set that a vegetarian, or maybe a clerical error, but whatever the case might be, we're going to assume it was a vegetarian, that individual was thrown into that group. And so we removed that value from the data set because it didn't fit. There could be a case where when we did a sample, we might have hit a big pocket of vegetarians, and then there's 1 or 2 people who are not vegetarians, and so we would have thrown their data points out for that particular sample. But you can see how those samples can be misrepresentations of the entire population, and that's what we're going to kind of talk about today. So with sampling error, we are first looking at the definition here. The sampling error is the error resulting from using a sample to estimate a population characteristic. So we can see the inherent difficulties with having a sample and using it to represent an entire population. So with example 1, we are talking about the IRS publishing their annual figures on individual tax returns in a document called Statistics of Income, Individual Income Tax Returns. For the year 2005, the IRS reported that the mean tax of individual income tax returns was $10,319. In actuality, the IRS reported the mean tax of a sample of 292,966 individual tax returns from a total of more than 130 million such returns. So the IRS's mean tax that they posted or published was not based off the 130 million returns that they had received. It was based on a sample of those 130 million returns. They only looked at 292,966 possible income tax returns out of the millions that they actually had in their possession. So we're just going to identify a couple of characteristics about this particular question. So for part A, it says identify the population under consideration. The population in this case, it's easy to say, oh, well, that's the U.S. population, but it's not the U.S. population because not every U.S. citizen files a tax return. The population under consideration in this case is actually going to be the individual tax returns working from home, and now you get to hear the dogs again. Individual tax returns for 2005. And then we want to identify the variable that we're considering in this particular example. The variable on that one is just the amount of income tax. And when we answer part C, I think that one is pretty clear because it's actually specified very clearly in the example. It says, is the mean tax reported by the IRS a sample mean or a population mean? So in this case, it is actually going to be the sample mean. And remember, our notation for a sample mean is X bar. Just a little side note, population mean, we want to make sure we are still up on our notation. Population mean is mu. Part D, should we expect the mean tax of the returns sampled by the IRS to be exactly the same as the population mean of all individual tax returns for 2005? Well, in that case, no, we cannot expect it to be exactly the same as the mean. This is a small sample, relatively small, compared to the 130 million returns that they received. It's a relatively small sample that is, the mean should probably be somewhat close, but it will not be exact. So we don't have an expectation. Should not expect the sample mean to be exactly the same as the population mean. And then how can we answer questions about sampling error? Well, for one thing would be you'd have to know what the distribution of all possible sample mean tax amounts would be. So that what that's saying is, if we took every conceivable sample of 292,966 returns, because there's obviously more than one, what would be the mean of all of those means? And I know that's kind of confusing to think about, and hopefully it'll make sense when we go into further examples. But there are I can't even begin to think of the number of possible samples exist of this size out of the 130 million returns that are possible. You could type it in the calculator, but I probably feel like you would get an overload error on the calculator because there are going to be a very large number of sample sizes of 292,966 out of the 130 million returns. So when it says part E, how can we answer questions about sampling error? For instance, is the sample mean tax reported by the IRS likely to be within $100 of the population mean? We need to understand the distribution of the sample. Of all sample means, which is X bar, for samples of size 292,966. So without knowing that, we can't really make too many assumptions about the values. But what this is called here, what we're talking about here in Part E, is what's called the sampling distribution of the sample mean. So we're taking means of means, and we can get a better representation of what's going on with the specific samples and the population that we are investigating. So Here is the definition for the sampling distribution of a sample mean. It says for a variable x in a given sample size, the distribution of the variable x bar, so that's our sample mean, is called the sampling distribution of the sample mean. Again, don't get too confused just yet. As we go through the examples, maybe things will start to kind of clear themselves up on their own. With example 2, that's where we'll kind of start looking at that. And this is a very small population that we're going to use because it's probably better to understand it with a smaller population first, and then we can go on to a larger population. With the 5 players on the basketball team, we have their heights, and that is the variable of interest. So our population is the basketball players on this team, these 5 players specifically, and then our variable is the height of these players. So when we're looking at example 2, and I apologize, there was I had to pause the video for a while there because I had a couple questions that were being asked of me. So we were talking about the sample mean of the samples of the players on this basketball team. So it says obtain the sampling distribution of the sample mean for samples of size 2. So I've gone ahead and put all this into a chart that we can look at instead of writing it all down. So in this first column, in column A, we have all the possible samples of size 2. We have player A matched up with the other 4 players, player B matched up with the remaining 3 players that he can be paired with, player C matched up with the remaining 2, and then player D matched up with player E. And I've listed in column B their respective heights for each individual in the sample. And then the sample mean is indicated in column C. The population mean, if we took all 5 players, added them together, divided by 5, we would get a population mean height of 80 inches. So the overall population mean, in this case, the exact mean of the entire population is 80 inches. But you can see from this column on the sample means that different samples yield different results. If we matched up player A and B, we get 77 inches. That is not completely accurate with the representation of the population mean. If you look at, let's say, when we paired up D and E, players D and E, their sample mean was 83.5, so it's 3.5 inches larger than the true mean. So this is where we come up with these sampling errors. The sample is not always going to be 100% representative of the entire population. For part B, it says to make some, I believe, let me see what it said again. Make some observations about the sampling error when the mean height of a random sample of 2 players is used to estimate the population mean height. So that we just kind of talked about that, but you can see that out of the 10 possible samples, we only have 1 sample that would actually give us the exact population mean. So that's a 10% chance that one of our samples will yield the exact population mean. We can also see that if we're looking at part C on here, find the probability that for a random sample of size 2, the sampling error made in estimating the population mean by the sample mean will be 1 inch or less. That is, determine the probability that X bar will lie within 1 inch of mu. So if we go back to the chart that we created here, we're looking for every possible sample that is within 1 inch of our population mean of 80. So we can, let's see, we have players A and E, we have players B and D, C and D, and that's it. Those 3 samples are the only ones that are within 1 inch of the true population mean. So there is a 30% chance that we will select a sample that is within 1 inch of the true mean of the population that we are studying. With example 2, we're using the same heights, the same players, but now we're looking at a sampling distribution for samples of size 4. We're going to make the same observations that we did before, and And then we're also going to find the probability that a random sample of size 4 will be within 1 inch of the population mean. So we're going to go back to the chart, and I have already added these in. So here in column E, we have the samples of size 4, all the possible samples of size 4. And then in column F, I have their heights listed. And then in column G, we have the sample mean from each one of those samples. Now, if we notice in this sample mean, none of our sample means are exactly the same as the population mean. But so that does indicate to us that there is sampling error that has occurred. But what we do notice, if you pay attention, is that there are 4 of these sample means that are within 1 inch of the population mean. Specifically, we have these 4 values right here, 79.75 through 81. Each one of those 4 samples, are within 1 inch of the population mean. So we can say that there is an 80% chance that a randomly chosen sample of size 4 will have a margin of error of 1 inch plus or minus with respect to the true population mean. And this is something we're going to keep building on. We're actually going to be able to calculate these sampling errors with a degree of certainty. But for right now, we're just looking at it in general terms to make sure that we understand how these things occur. So if we move on to continue through our notes here. So what I've put together here are several dot plots. The first dot plot is a sample size of 1. So that's just taking each one of the individual basketball players. Their height would be the mean. Then we have sample sizes of 2, sample sizes of 3, sample sizes of 4, and sample sizes of 5. What I want you to pay attention to is that vertical blue line, that dotted blue line down the middle of the screen. That is our population mean. And you can see that as our sample sizes get larger, these values for the means of the individual samples start to cluster tighter and tighter and tighter around that the true population mean. Eventually we do get to a sample size of 5, which is the entire population, and it is exactly on the population mean. But when we look at a sample size of 4, we have a tight cluster. With a sample size of 3, it's still pretty tight cluster, but it's starting to spread out. And then we notice that here with 2, and then again with just 1. So the closer we get to a sample size that is representative of the population, the better our information is going to get. But we've also discussed that there's a lot of situations where sampling surveying the entire population is not practical. The IRS, for example, at the beginning, they would not want to compute the mean of all 130 million tax returns. It's easier to just get a representative sample. There will be errors. We can see that now, but we can also see how we can account for these errors, which again, like I said, is something we're going to build upon as we continue through our notes. This table right here kind of breaks down the dot plots. We have the first column is the sample size. Again, we're talking about the players. The number of possible samples that exist within each sample size. Then the number of those samples that are within 1 inch of the population mean. So over a sample size of 1, we have 2 samples that are within 1 inch of the population mean of 80 inches. For sample size of 2, it's 3, and we can go on down. So, and then this fourth column is the percentage of those that are within 1 inch of the population mean. So for sample size of 1, we just take 2 divided by 5. We get 0.4, which is 40%. The last 2 columns, I kind of even restricted it even tighter. We're looking at within a ½ inch of the mean. And we would get, in this case, for sample size of 1, there are 0 samples that are within a ½ inch of mu. But then we start moving on down the line. We get 2, 2, 3, and then 1 in that last row, because that is the entire population. So there can only be 1 sample. That is the entire population. So that leads us to this next conclusion. The larger the sample size, the smaller the sampling error tends to be in estimating the population mean. It just makes sense. We used a very small population to illustrate what we're talking about with sampling errors and sampling means and sampling distributions. But when we're doing this in practice, that's not very practical. You're not going to have small populations. You're going to have large populations. And so you have to come up with sampling methods that account for the errors that you would encounter with sampling. And it helps you determine what size of sample you might need from a population, given the population size, to get a better representation of what you want to do. So that kind of leads me to when we were talking about doing our project, which I think probably has been scrapped at this point. But I wanted you guys to think about, how would you generate your samples? How would you be sure to get an accurate representation of the entire student body without actually surveying the entire student body? That wasn't the purpose of the activity, was to survey everyone. It was to find a representative sample. So be thinking about what you would have done had this project continued, and you're going to start to get a better intuitive feel for how sampling and sampling errors kind of come into play when you are discussing an entire population. The homework should not be difficult, I don't believe. For 1, 2, 3, 4, you're going to just do exactly what we did in the examples. You're going to set up their specified number of sample groups, find their individual means, compare that to the population mean, and answer a few other questions. So like for part B on 1, 2, and 3, construct a table. We've already done that, so you know how to. For part C, for each sample size, find the probability that the sample mean will equal the population mean. And for part D, for each sample size, find the probability that the sampling error made in estimating the population mean by the sampling mean will be 0.5 or less. Part 4, we're talking about the Los Angeles Lakers. I had to bring Kobe in. We haven't used Kobe in any of our problems, and now we should. Why not? I know you see a lot of repeat parts B through D there. Don't stress out. Hope everybody's doing great, and I'll be talking to you guys soon.